Hello, good morning, students, friends. Today we will continue from the dimension analysis. It is almost already over. We left at an example velocity v is equal to meters per second, that can be written in terms of L divided by T, that is equal to L multiplied by T to the power of minus 1. Velocity v is equal to L multiplied by t to the power of minus 1. Any fundamental quantities are primary quantities such as length, mass, time and temperature, represented by capital M, capital L, for time capital T, and temperature theta. They are known as fundamental or primary quantities. Then whatever we get in dimensional analysis, we call it as derived or secondary quantities. For example, one more example we will take and complete that, and then we will come to flow around submerged bodies, introduction, practical examples of submerged bodies. Okay. In dimensional analysis, if you want to write discharge Q, that we know is nothing but area into velocity, where area is equal to L squared multiplied by V meters per second, that is L divided by capital T. This can be written as L cube divided by T, which is also equal to L cube multiplied by T to the power of minus 1. This is dimensional analysis because we are using the primary quantities length, time, to get the value Q in meter cube per second. Meter cube per second. So meter cube is represented by L cube second in T to the power of minus 1. Okay. This completes dimensional analysis. That means derived quantities are always known as dimensional analysis. Now, we will continue these practical examples of submerged bodies. Whenever there is a relative motion between a real fluid and a body, what is real and ideal fluid? Ideal fluid in which viscosity is absent, whereas real fluid is the one viscosity present. The fluid exerts a force on the body. The body exerts an equal and opposite force. Suppose if I push you, your body also push my hand. If the body is moving at a constant velocity in a stationary fluid, the fluid motion is unsteady. Unsteady because at a given point in space, the velocity changes with time. However, if the body is stationary and fluid flows at a constant velocity, it is steady motion. The magnitude of the force is same in both the cases. Whereas a body wholly immersed in a real fluid may be subjected to flowing two kinds of forces due to relative motion between the body and the fluid. You see the figure. It is an aircraft wing. There is a velocity, uniform velocity of fluid u meters per second. Drag force, the component of force in the direction of flow on a submerged body is called the drag force. Means whenever this fluid is acting on the body, there will be a resultant force exerted on the body that can be resolved into two components. That depends upon what is the angle with which acting with respect to horizontal. We can resolve FD in horizontal direction, that is in the flow direction, FL perpendicular to the flow direction. Then the component of force in the horizontal or flow direction is known as drag force, denoted by capital F suffix capital D. Lift force, the component of the force at right angles to the direction of flow, is called lift force, denoted by FL. When a free stream approaches the body along the axis of symmetry, the force acting on the body is only the drag force in the direction of flow, and there is no lift force. The production of lift force requires a symmetry of flow, while drag force exists always. It is possible to create drag without lift, but impossible to create lift without drag. That is nature. We can create, it is possible, drag without lift, but it becomes impossible to create lift without drag. There will be some drag, always will be there. Then only it is possible to create the lift. So without that it is not possible. That is the meaning. The fluid viscosity affects the flow around the body in three ways to cause the force on the body. They are: at low Reynolds number Re, denoted by Re, the fluid is deformed in very wide zone around the body, causing pressure force and frictional force. As Reynolds number increases, when it was low, it causes pressure force and frictional force. As Reynolds number increases, various effects are confined to the boundary layers, causing predominantly only friction force on the boundary. So definitely this frictional force and pressure force are more dependent on Re. If it is more or increases, then naturally it confined to the boundary layers, causing predominantly only friction force. Only friction force on the boundary. For certain body shapes, the boundary layer can separate, causing additional pressure. You will stop here. Additional pressure. Figure shows a body held stationary in a stream of real fluid moving at a uniform velocity u. We will find out expression for drag and lift. You refer to this figure. Velocity u, uniform velocity of fluid, which is acting on a body, which causes a force resultant F in this direction. It can be resolved into two components, Fd and Fl. Fd here, Fl here. This is a perpendicular component. Now let us consider a small element, the area dA. Let us assume PdA is the force acting depending upon the theta, that is flow of fluid with respect to this tangent. Now we will consider this small elementary area dA here in a free body diagram. We will get the forces. Forces we are getting PdA cos theta, that is acting downward, whereas shear force is acting upward, that is for lift component. For drag component, horizontal component of pressure force, that is PdA cos theta, and tau naught dA cos theta, both are acting in the same direction as far as drag component is concerned on that elementary area dA, whereas lift force are acting opposite to each other. On an element of area dA on the surface of the body, let P and tau represent the static pressure and shear stress, and let theta be the inclination of the tangent to the element with the direction of flow, as I have shown there. The component of the force due to pressure and shear along the direction of motion is known as drag force Fd, while the component perpendicular to the direction of the motion is known as lift force Fl. Let theta is equal to angle made by the pressure force with horizontal direction. Drag force Fd is equal to force due to pressure in the direction of fluid motion plus force due to shear stress in the direction of fluid motion. That will be equal to P dA cos theta plus tau naught dA cos 90 minus theta, that is sin theta, which is equal to sin theta. Now total drag Fd is equal to, we have to integrate because we have taken elementary area, we should integrate to get it summation of P dA cos theta plus summation of tau naught dA sin theta. We will get integral P cos theta dA plus integral tau naught sin theta dA. The term integral P cos theta dA is called the pressure drag or forearm drag, while the term integral tau naught sin theta dA is called the friction drag or skin drag, or also known as shear drag. We will stop here. We will continue in the next class. Okay.